Good afternoon, everyone. This is Mr. Couple. Today I'm here with my IB Physics HL Year 1 class, and today we'll be learning about electric currents. This is the handout that we're going to be completing today. This lesson should take no more than 30 minutes. The IB objective that we're looking at today, the applications of skills that you should be able to solve problems using the drift speed equation. So that's what we're going to talk about today is the drift speed equation for electrons. Now, before we start talking about electric current, which is the rate of flow of charge through a wire, I want to first talk about how do you even get charges to flow through a wire in the first place. So I have to mention you guys this concept of free electrons. And I couldn't put this on the handout, so I'm going to show you guys some animations instead. Okay, so first up, we should talk about the difference between a conductor and an insulator. So an insulator is material that resists the flow of charge, whereas a conductor is material that allows the free flow of charges. So you'll notice that if you study the atomic structure of an insulator versus the structure of a conductor, what you'll find is that in a conductor, the atoms have a lot of extra electrons. And these are like valence electrons that are really far out, and they're like really loosely held onto the atom. So they're far out in their orbits, and so the atom, the nucleus, can't really exert as much of a force on them. And so these electrons tend to just kind of drift around between atoms. Like one atom will grab onto it, it'll move to another atom. They're just kind of free to move around. Whereas in an insulator, you have very little, if any, electrons that are freely moving between the atoms. That's the difference between an insulator and a conductor. So remember that what happens is you actually imagine that these free electrons then are just kind of moving around and they're exchanging. Whoops, where did I put the picture in? They're just kind of freely moving around from atom to atom, just going all over the place. And these electrons move randomly, like the molecules in a gas. And you'll notice that every now and then they're like bouncing off or you know scattering off the atom. So that red dot is the nucleus, like the core of the atom, and then the blue dots are the electrons sort of moving around between the atoms. So this is what a conductor looks like. These electrons are just randomly moving in all directions, so there's really no net flow in any one direction. They're just randomly moving. So then the question is, what happens if we put an electric field in the presence of these electrons? And so we talked about last class, someone should answer this question when I ask it. What does an electric field do to an electric charge? This is our last lesson. So if I got an electric field here, what is it going to do to these electrons? Electrons have a charge. So what does an electric field do to a charge? Somebody.
They're, they're going to flow in that direction.
No. What does a field do to a charge?
Wait,
Doesn't it apply force towards the charge?
It applies a force on the charge. That's exactly what happens.
I tried to say that, but I don't think it came out.
So
Push to talk is cursed.
charge Q times electric force strength E gives you the strength of the force. Okay, now here's the thing. So the field is pointing to the left, but electrons have what charge? Charge an electron, you guys.
Negative.
Negatively charged. Electrons are negatively charged. So electrons have a negative charge. Now the way we define the electric field is it's the direction that a positive charge would move. But electrons are negative charges. So guess which way they're going to move as it relates to the field direction. Electrons always go in the
Opposite.
they go in the opposite direction to the field. So the field shows you where a positive will be moved or pushed. So electrons go the opposite direction. So now instead of these electrons just kind of randomly going in every direction, there's no net flow in any one direction. They're just randomly going all over the place. So that's what happens when you just have a regular conductor. The free electrons are just randomly moving everywhere. When we stick a field in that conductor, all the electrons are going to line up and move the same direction, and they'll move opposite to the field. So electrons flow opposite to the field. They all line up and they're all going to flow the same direction. We call this direct current. When all the electrons are flowing the same way, we call that a direct current. There's another type of current. Does anyone know what it's called? It's called alternating current. So direct current is DC, and then the alternating current is AC. So what happens in an alternating current is the direction of the electric field rotates, so it like flips. So in the United States, when you plug something into the wall, the electric field in the wire is going to flip 60 times per second. So in 60 seconds, the field will switch back and forth between pointing left, right, left, right, left, right, left, right. It'll switch 60 times per second. So the result is that the electrons, instead of all moving in one direction, the electrons actually oscillate like a spring. That's what happens in alternating current. We are not going to study alternating current at this time. We're just going to be focused on direct current. Okay, part B, explain with reference to the electric force what happens to the free electrons when an electric field is applied across a conductor. So basically, I want you guys to answer this. So what we just said was that the electric field exerts a force on the electrons. And then this causes every single electron to move in the same direction, which creates a current. So just for some tips, we're first going to say that the E field, you're going to say exerts a force on the electrons. And then the next thing you need to do is like talk about current is created. So I'm going to have you guys answer that in a more, complete sentences, but I'm just going to leave you some notes there. So the E field exerts a force on the electrons, and then a current is created. So the question is, what does that electric field look like? So it turns out when you create an electric field inside a conductor, it follows the shape of the conductor. So here you have a wire made of copper or some conducting material. The electric field will actually follow, like if you bend or twist or deform the wire, the electric field will bend and twist and deform along with the wire. So no matter where an electron is in this wire, it's gonna feel the electric field and it's gonna get pushed by it, and that electric field will drive the electrons and push them through the wire. So the question that we have is, how fast do the electrons move, and can we figure out a way of quantifying how fast they move? So to do that, we have to create this new physical quantity. It's called the electric current, and the symbol for electric current is capital I. And this is all new. This was not taught in ninth grade. So the electric current is defined as the rate of flow of charge through a cross section of the wire. So that part about where it talks about the cross section. So if you look in this picture down below, that's this part of the wire here. That's the cross section. So we're saying how many charges, like what amount of charges, pass through that cross section per second. So just roughly like to have a discussion here, if you guys want to chime in, there are two things that affect the amount of electrons that pass through that cross section. So what are the two things you guys can think of? Here we have all these electrons moving through a wire, right? What are two things that determine the amount of electrons that are going to pass through this area here?
The material and like how good of a conductor it is.
Okay, so what I'm just thinking, so what am I trying to say? What would that change if it was a good conductor versus a bad conductor? What would that change about the configuration of these electrons? So remember the picture? Good conductor versus bad conductor. What happens to the electrons? Bad conductor, insulator, good conductor. What happens to the electron configuration? You guys are super quiet. It's because we're online. You guys are scared to talk. A good conductor will have more free electrons. So you'll have a greater number of these electrons. And so think about it. If there's a greater number of them, then how many are going to pass through the cross-sectional area? More of them. There's a second thing that will affect the number of electrons that pass through this area. So the first thing we found out was that it's n, the number of electrons. And what's the second thing that will affect how many electrons pass through that area per time? It's related to this up here. What happens if there's a stronger electric field? Come on, guys. Should I just stop asking questions? Like you guys are super quiet. No one's responding.
Stronger electric force is stronger force in general.
Stronger force. And then what happens? If I push these guys harder, if these guys are getting pushed with a greater force, how are they gonna behave?
Move faster.
They're gonna move faster. What happens if they're moving faster? Then we're gonna see more of them.
Greater rate passing through the cross section.
There'll be a greater rate of charges passing through this cross section. All right, so that's the second thing that we're going to talk about, which is V. Whoops. And then we call that the drift velocity. The reason we call it the drift velocity is because the electrons don't flow through the material perfectly. Like every now and then they'll like bounce off the lattice atoms or the atoms that are inside the material. And so it's not going to be like a perfect flow of charge. They're going to be kind of like boom, 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 like kind of moving all over the place, but there'll be a general net flow in one direction. Okay, so current is defined as the amount of charge. So it's how much charge passes through the cross section per time. So this is the amount of charge and then this down here is the time. Okay, so before we start, we have to come up with a variable that will tell you how good a conductor is, and that is little n. So when we're doing these types of problems, you'll see this symbol n. It's called the charge density. So the charge density is roughly telling you how many free electrons there are, and the charge density is expressed in electrons per unit volume. So that's the charge density. So little n, if I write this down on the margin over here, so little n is roughly big N divided by the volume. I'll put volume and put serif on the volume so that you can see that it's a volume and not a velocity. So the charge density is the total number of charges per unit volume. And so for conductors, this number is going to be higher than for insulators. So insulators will have a low charge density, whereas conductors will have a higher charge density. Here's what we want to do. We want to determine the distance the electrons travel in time delta t. So this is very simple. We know from basic physics that distance is equal to velocity times time. And so what we want to do is we want to just figure out what that distance is. Well, that's it. So what we're going to imagine is that you have like a cone. So I'm going to draw a cone here. So imagine we have this, that's not it, what's this called? This is called a cylinder. I don't know why I'm calling it a cone. So imagine you have this cylinder, and the basic idea is that any electron that's within that cylinder will be able to travel this distance in that amount of time. So it's V delta T. So if there's an electron in this cylinder here, anywhere within this cylinder, it will make it and pass through that cross-sectional area in the time delta T. So that's just it, right? Distance equals, velocity times time. And so we are saying that D is going to equal to the velocity times this time, which we're calling delta t. Delta t means it's like some short time. So when you do calculus, you'll call that an infinitesimally small time, dt. But in IB physics, we use delta t. So there's just some small amount of time, delta t, that's passed, and we'll say, all right, the electrons will travel this distance d. Where if they travel faster, there'll be a greater distance. So if the electrons travel faster, then the height of our cylinder will extend further and more electrons will pass through. If the velocity is slower, our cylinder will have less height and then less electrons will pass through. Next question, how many free electrons are contained within a volume of wire of length d? So how many free electrons are there within the volume of this wire? So we know over here that n, the charge density, is the number of electrons per volume. So if we want to find the number of electrons, we just have to multiply the charge density times the volume. So what is the volume of a cylinder? You guys know the volume of a cylinder?
Yeah, let me Google that.
This is one that you should just know. The way you find the volume of a cylinder is you take the area of the base and you multiply by the height. We have done this before when we talked about pressure. We derived this equation. Volume is, this is not velocity, this is volume, so I'll put my serif on there. Volume is area times height. So for here, for NV, for the V, I'm going to substitute in A, and now the height of my cylinder is not H, it's D. That's the height of the cylinder, so it's D. But we just said that D was equal to V delta T, so we can get down this equation that says the total number of charges that will pass through the cross-sectional area is N times the area times V times delta T. And then this V is lowercase v, like this is actual velocity. So I'll try to curl it. Let's try that one more time. I'll make it look like a V. Okay, there you go. So nav delta T. Okay, so this is the total number of particles, not particles, electrons or charges. This is the total number of charges that will pass through the cross-sectional area in unit time delta T. So that's up here, that's our delta Q. So if we want to find the current, we just have to take that quantity of charge and divide by the time. But it's going to be a little bit more trickier than that. So this is a number of charges, but if we want to find the actual amount of charge, we have to multiply that by the charge of each electron. So one electron, so I'll show you guys here. So I'll draw a picture of an electron. So a single electron, we're going to say that it has charge Q. So if there are n electrons, then you should realize that how much charges we have is NQ. So the total charge, if you have n electrons, then the total charge is going to be N times Q will be the charge. So one electron has charge little q, so n electrons has charge NQ. Okay, so now let's find the current. To find the current, we need to take delta Q over delta T. Okay, so we just found the amount of charges that pass by. It's NQ. But N is a super complicated equation up there. Why don't I just write it as NQ over, and Q is the charge of an electron, over delta T. Okay, so now we're going to substitute in this value of N into there. So we're going to get little NAV delta T times Q divided by delta T. And then we can see that the delta T's will cancel out. And then we get this equation that says the current, the rate that these electrons flow is going to be equal to NAVQ. And then realize that Q is based on what type of charge you have. So we call that the charge carrier. For the situation of charges moving through a conductor, the charge carrier is always going to be the electron. And so you'll put in the charge of an electron in there. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. I'm not going to talk about that until a little bit later. So that's the derivation of this equation. This is called the drift velocity equation because it has the drift velocity inside there. The V is the drift velocity. So from this, you can determine how fast the electrons are moving through the wire. So we'll return to this in a little bit, but basically we have found the current through a wire is NAVQ. Okay, let's talk about units before we confuse ourselves. The unit of electric current is called the Ampere, capital A, and it's one of the fundamental units of the SI system. But it's kind of weird. Let's define it. So how would you define an ampere? So an ampere from this equation is a charge per second. So it's a charge per time. So the ampere, so I, current, equals delta Q over delta T. So what we could say is that 1 ampere is equal to, and now the unit of charge is a coulomb. So it's 1 coulomb in 1 second. So 1 ampere is 1 coulomb per second. So we could say that the ampere is defined. So an ampere is defined as a coulomb per second. But the ampere is the actual SI unit. We don't use coulombs. Coulomb is not an SI unit. Ampere is the SI unit. The reason why is, we'll talk about this when we get to the magnetic force lesson, but it turns out that if you have two wires that are both carrying a current, they will actually either attract or repel each other. And so that's why we base the ampere as an SI unit, because it's more it's easier to use it. It's more relevant. That means that actually the SI system, the international system, defines the coulomb in terms of the ampere. So what would be a coulomb? What would a coulomb be in terms of the ampere? So if an ampere is a coulomb per second, we just need to multiply both sides by seconds, and then you'll have what the coulomb is. So if an ampere is a coulomb per second, if we multiply both sides by seconds, then you can see that a coulomb is equal to 1 amp seconds, an amp second. And you guys have probably heard of this before, maybe like not in these units, but maybe you've heard of like milliamp hours. Have any of you guys ever heard of that? Milliamp hours?
Like in batteries.
Like in batteries. So that's a unit of charge. So when you give an amp time or an ampere times a time, that's giving you an amount of charge. So if you've ever read on a phone battery or any sort of battery, it'll tell you like milliamp hours. You can actually calculate the number of charge, the amount of charge that that battery can hold. Maybe that'll be a fun problem that I can give you guys sometime. Okay, so just remember that the coulomb is the unit of charge, the ampere is the unit of current. Okay, now let's do the problem that I've been hyping you guys for. Calculate the drift speed of the electrons in a copper wire. So we're going to take some reasonable data for a copper wire. So we're going to say that it has a diameter of 0.65 millimeters. So this is a tiny little wire, maybe like, the wire that'd be in like a speaker cable or something like that, like a little tiny wire. The diameter is about a little less than a millimeter. So it's this really thin wire. The current that's flowing through the wire is a quarter of an amp. And it's going to give us the charge density of copper. The charge density of copper is 8.5 times 10 to the 28 free electrons per cubic meter. So the reason why that number is so high is because a cubic meter is a huge volume. Like that's a meter by a meter by a meter. Like that's a lot of space. So you're gonna have a ton of electrons. 8.5 times 10 to 28 electrons in a cubic meter of copper. And then lastly, I'm giving you the charge of an electron. So the charge of an electron is 1.6 times 10 to the negative 19. So that's going to be Q in our equation. The charge of an electron is 1.6 times 10 to the negative 19. Okay, the first thing is, annoyingly, if you look at the equation, so I equals NAVQ, the annoying thing is that the equation is in terms of A, but the problem has given us the diameter of the wire instead of the area of the wire. So the first thing we have to do is we have to figure out, well, what's the area of the wire? Everything else was given to us. We know the free electron, the density, the electron density is N. We know the current, and it told us the charge. What we don't know is the area. So the first thing we have to figure out is what's the area. So let's calculate that over here to the side. So we've got our wire. So I'm gonna draw a picture of a wire. So here's the wire. And it told us that the radius of this wire, or wait, what did it give us? The diameter. It said the diameter was 0.65. So from here to here was 0.65 millimeters. And so what we want to figure out is what's the area. All right, so the area is equal to pi r squared. So the area of our wire is going to be pi times the radius. So the way you find the radius is by taking half the diameter. So if I take half of 0.65, and then I don't want to write this in millimeters, I want to write it in meters so that the numbers will work out. So it's going to be times 10 to the negative 3, and then I have to square that. And so now this will give us the area, the cross-sectional area of the wire is what this is called. So I'm going to take pi times 0.5, nope, I need a parentheses. So parentheses times 0.5 times 0.65 times 10 to the negative 3, and then I need to take this whole thing and I need to square it. And so the area is 3.32 times 10 to the negative 7, and then this is going to be square meters. And then we should get a really small area because this is a really small wire. Meters are big, this wire is small. So we're expecting to get this really small number. That's why it's only like a millionth of a cubic meter. It's a small area on this wire. Not cubic meter, square meter. Jeez. Okay, so now I just have to take that area and then substitute it into the equation, and then we will have the velocity of the electron. So we're trying to solve this for V. So if we solve for V, we're going to see that V is equal to I over NAQ. Now we have everything that we need to know. So it told us that the current was 0.25 amperes. Told us that the number of free electrons was 8.5 times 10 to the 28. There's no unit on that because it's just a number. Okay, next we have the area, which is 3.32 times 10 to the negative 7. Those are square meters. And then last I have to multiply the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs. Ran out of space. Okay, now remember that the ampere is actually, we set up here, it's a coulomb per second. And so since this is a coulomb per second, if we look at what happens to the units here, let's find out. So we're going to have, let's see. So the per seconds are going to cancel out. No, what am I doing? Why am I canceling the per seconds? Coulombs are going to cancel out. So coulombs here, coulombs here. Okay, then what else? I'm having problems. Why isn't the meter? How do I have meters squared? I have meters squared per second. What am I doing wrong here? I haven't made any mistakes. I don't know what's going on. Oh, anyway, let's just calculate what this answer is going to give us. So did I? Yep. Okay, so I'm going to take this number here. I'm going to put 0.25 divided by 8.5 times 10 to the 28 multiplied by that area that I had from before multiplied by 1.6 times 10 to the negative 19. And I get that, which is the correct answer. I don't know why. I'm not seeing the units work out, which is kind of strange to me. So we get that it's 5.5 times 10 to the negative 5 meters per second. Okay, what do you guys notice about that speed?
Very slow.
It's super slow, yeah. Oh, I just realized where it's because this number here is per cubic meter or per square meter. This is wait, this is per cubic meter. So this is meters to the negative 3. Okay, I found it. So that's the number of charges per cubic meter. And so you can see there that the square meter and the cubic meter almost cancel out. So you actually end up with the units of being seconds negative 1 divided by meters to the negative 1. And then that gives you your meters per second. Okay, there it was. So this number had units on it. That's the mistake that I made. Okay, cool. I'm glad I found it. Okay, this is crazy, 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 crazy slow. So electrons move really, really slow. When electrons move through wire, they move very, very slow. And you have to kind of think about this like this poses a problem, right? Because why is it then when I flip a light switch that the light turns on almost instantly? It turns on near instantly. So what you have to realize is that it's actually not the electrons that travel through the wire. The electrons themselves move really, really slowly. Like if I thought about how long does it take, if you look at like your laptop plugged into the wall or your phone plugged into the wall, if you have a cord that's like a meter long, it'll take about 5 hours for an electron in a direct current to flow through 1 meter. So if you have a wire that's 1 meter long, if a direct current is flowing in that wire and you have an electron here, it would actually take 5 hours for that electron to reach the other side of the wire. That's how slow electrons move. They move extremely slowly. So when you flip the light switch, it's not like you have to wait for those electrons from the switch to travel to the light bulb. What happens is that the electric field is established at the speed of light through the wire. And as soon as if your light bulb is over here if that's where your light bulb is, there's electrons in that wire everywhere. And as soon as you establish an electric field in that wire, the electric field gets established across the wire at the speed of light. So when you flip the light switch on, that electric field goes zoop, zoop, zoop across the wire. And now that electric field is basically everywhere in the wire. And so all the electrons all start to feel that force all at the same time. And so it's not like you have to wait for the electrons to travel to your device. That's not what happens. The electric field is going to push the electrons everywhere in the wire at relatively the same time and make them all start to move at the same time. So you'll be able to transfer that energy through the motion of the electrons nearly instantly. I mean, it's at the speed of light, but I'm calling that nearly instantly because we can't really tell the speed of light if you're in a room flipping a light switch. Okay, last question. Suppose instead the wire were made of germanium, which is a semiconductor. The number of free electrons in 1 cubic meter of germanium is about 10 to the 9th times less than in copper. 10 to the 9th times less. So there are way fewer free electrons in germanium because it's a semiconductor, which means a semiconductor can sometimes be a conductor and sometimes be an insulator. Like you can kind of control, you can decide whether it's going to be which one. So it's kind of like an in-between space. That's what a semiconductor means. Calculate which radius. Yeah, it says calculate what radius of germanium wire would be required to sustain this current with the same drift speed. So if we wanted to push 0.25 amps through germanium wire with the electrons moving at the same speed as they do in copper, then what radius would we need of wire? Okay, so we're going to set this up the same way, except what's going to change is that we are trying to find the area this time. So we want to find the area. So area is going to be equal to I over NVQ. So let's go ahead and calculate what that area is, and then we'll go backwards and find the radius from that. So same current, 0.25. But now the n is going to be less. So instead of 8.5 times 10 to the 28, we're going to have to subtract 9 from that. And multiply by by the drift velocity we just found, which was 5. See if I can get another sig fig on there. 5.54. And then the same charge of electrons, which is 1.6 times 10 to the negative 19. Electrons have a very small charge. What we should say is a coulomb is a large amount of charge. Like a bolt of lightning has like 15 coulombs. So a coulomb of charge is a lot of charge. I don't like how that line is crooked. Oh, I didn't set a timer. I'm probably over on time, aren't I? Okay, so let's find what this is. Calculator, here we go. So I'm going to keep that in there. Okay, 0.25 divided by that number, the drift velocity times 8.5 times 10 to the, I'll just do the 28 minus 9 right here, 28 minus 9. And then I'm going to multiply this by 1.6 times 10 to the negative 19. What did I do wrong? Oh, I guess you're not allowed to do that. That little trick I did there with the E, you can't do that. So let's see, what is 28 minus 9? Is that 19? Someone who's better at math than me, help me out here.
28 minus 9.
Isn't that 19?
Yeah.
Okay, good. That can't be right. I don't trust this at all. Let's see. 0.25 minus that. How is that possible? I should have a very small area. Oh, it's because the answer is messing everything up. Okay, let's do this one more time. So I need this number. Okay, I'm going to have to put this all in again. Okay, so 0.25 divided by 8.5. So I knew that was wrong. I knew I was messing up my calculator because there's no way that the area would be that big. That's a huge area. Our wires are not going to be that big. I mean, I guess it's a semiconductor, but that still seems like it's way too big. Negative 5 times 1.6 times the negative 19. I'm still getting that number. I mean, okay, big ass wire. Okay, fine. So 332 square meters. That seems like a huge area to me. All right, so now to find the area, so area is equal to pi r squared. So if we want to find the radius, we're going to need to take divide both sides by pi and then take the square root. So the radius is going to equal the square root of the area divided by pi. Okay, so I'm going to take the area here. I'm going to divide it by pi. And then I'm going to take the square root of that. And so I get 10 meters. That's crazy. So that wire that with copper was only 0.65 millimeters. With a semiconductor, it would need to be 10 meters. Oh, wait, no. It would 20 meters, right? Because that's the diameter. So the radius is 10, so the diameter would be 20. So with copper, you can make the wire like a millimeter thin, whereas if you tried to make the wire out of germanium, you would have a wire that's 20 meters across. So that's why we make wires out of conductors and not semiconductors. All right, the last question here is just something for you guys to solve on your own. I'm going to put this as I'm going to give you one fewer questions on the other page. I want you guys to do this on your own, but I'll set it up for you guys. So the way it works is that I equals to NA VQ, which is going to be constant. So the current in a wire. So if you've got a potential difference, which is what we'll study next time, but if I've got like if I've got a negative charge here and this is correct. If I've got a positive charge here and a negative charge here, like I connected this wire across two batteries, and then in one spot the wire is big and another spot the wire is small, what I want to know is how does the drift speed at A compare to at B? And so the current has to be constant. And this is because of conservation of charge. The number of charges that pass by point A have to be the same as the number of charges that pass by point B per second. And it's something called conservation of charge. If they weren't the same amount of charges passing by per second at A and at B, then you would have more charge coming in than it's going out, which is impossible. There always has to be the same amount of charge that comes in and the same amount of charge that comes out. It's conservation of charge. It's one of the fundamental laws of physics. So the current in a wire will always be the same across the entire length of the wire. So that's why I said I equals NAVQ equals the constant. But now notice what's changing is that the area is changing, but the charge carrier, electrons, are staying the same. The material is staying the same, so same charge density. So then that means that the velocity will change. So if NAVQ is equal to constant, then you can realize that AV is also equal to constant. So I just divide by N and Q. Well, N and Q are constant. So you see that AV is constant. So what happens if we, what does it say? State whether the electron drift speed at B is smaller than, equal to, or greater than at A. So looking at B, what happens in B in this equation right here? So B has, it has a greater area at B than it does at A. So the area at B goes up. And so since AV has to stay constant, then what has to happen to V is it has to drop down. So when the electrons go into this bigger, they're going to slow down when they get here. So electrons slow down. So when the wire gets wider, the electrons can slow down. Okay, that's it, guys. Have a great day. I'll see you later.